Alright, now we're going to be looking at a very specific class of functions which are called hyperbolic functions. And in general, they're of the form a some constant a divided by x to the power of n. But in this case, we're going to be looking at a very simple one where we have 1 over x. Now, if we're going to plot this, we know that if you choose positive values of x, then as you go to infinity, this is going to become very large, and if you divide 1 by a very large number, this is going to become 0, so it means it's going to go like that. But if you approach 0, then that means that for positive values of x, this is going to get a lot smaller, and we know that when this value x is less than 1, then that means the value on the top is going to continue to increase. So that means this is going to go up and up and up, and if we essentially try to take a limit as x approaches 0, then of this function, we would essentially get infinity. But there's a very subtle problem with this function, and it is that we have only considered the fact that we're approaching it for all positive values of x. What happens if we start looking at it from the perspective of all negative values of x? Well, in that case, you would start by choosing values like minus 0.1, then minus 0.01, and as you go along, these values are getting larger, but they're going towards negative infinity. So it turns out that if you take a limit as x approaches 0, but from the negative side of this function, then you're going to get minus infinity. But if you approach it from the positive side, you're going to get plus infinity. So what is the deal here? I mean, it is sort of defined. We know that it's going to be infinity in some sense, but look at what we have here. The limit of the function y as x approaches infinity, approaches the value 0 from the positive side, is not equal to the limit of y as x approaches 0 from the negative side. And basically, if we have this condition not being satisfied, it means that the function has a discontinuity. It has a discontinuity at x equals 0. Because essentially it is undefined. The only thing we can say is that the limit as x approaches 0 is undefined because it depends on which direction you're looking at it from. And this is true for a lot of functions that have this sort of property where you choose values of x that are negative, and then you're going to have this kind of thing. Now, what do you think is going to happen when you choose something like 1 over x squared? So let's try and plot the value of the function 1 over x squared. Now, we know that this is going to increase. It's going to be even steeper, so it's going to look like this for all positive values of x. We're going to have something like that. It is going to approach infinity. And if we look at it from the other side, if we plug in any negative value of x, once you square it, it becomes positive. So instead of having the curve coming down like this, you're going to have the curve going up like that. So in the end, it's going to look like a volcano, but it is going to converge at some point if you go far up enough. So let's look at it from two perspectives. Let's go from the right and from the left towards 0. So limit as x approaches 0 from the positive side of this function, well, that's going to be positive infinity. And the limit as x approaches 0 minus is going to be equal to it's going to be equal to positive infinity once again. Even though the property is satisfied, if we really think about this function, the question remains, is this function continuous? Well, that's kind of a very philosophical argument to make, and I'm pretty sure that anyone who is a mathematician would know that we cannot really say it is continuous, because if you really think about it, you're going to infinity. However, the function is not necessarily connected at the point x equals 0, because you can imagine it this way. You have the function coming up like that, and then coming up like that, and then at some point it's going to become almost completely vertical. So there's nothing telling us that the function is ever going to be connected at that point, and if it is not connected, then you have a discontinuity. So in general, we will claim that this function is actually discontinuous at x equals to 0, but of course we have to really think about it in terms of the function itself, because there's really no other way of thinking about it. It's just a fact of, does it make sense to say that the function is continuous? And it would be if you actually saw a peak like this. But that doesn't actually happen, because this is not that kind of function. Therefore, in this case, we would say somehow it is undefined. So we have to assume it is discontinuous, because there's no proof that it is connected at that point. And that sort of gives you the idea of what discontinuity means in terms of functions that can have different values, or maybe approach the same value, but due to the nature of those functions themselves, due to the fact that perhaps they're not really connected in a very proper way, they actually end up having discontinuities at a specific point.